So if we get started with this one, again we're trying to find the shear force and bending moment not at a point but as a function of x. So I've just kind of arbitrarily shown a cut here x. And just like we've been doing previously, what if I, again, imagine the structure cut at that distance x, and I'll just identify the left side and the right side. So let's talk about the left side. First of all my dimensions are in x. That's going to be easy. And my loading is a triangle. We've handled triangles before. But you'll notice that I've got to find all my reactions at A. Okay, so about the right-hand side. Well, first of all, I don't have any reactions. My distances are different. What's the length of this segment? If this segment on the left side is x, what's this segment here? Well, the total length is 20, so this is going to be 20 minus x. So as x moves around anywhere it wants to go, the left segment will be measured x, the right segment will be 20 minus x. So now all my dimensions of this side, not only is it a trapezoid, but they're going to be in terms of x of 20 minus x, might be a little messy. So I'm going to suggest today, or this first start problem, that we go to the left side. Even though we have to find reactions, I think reactions are going to be not as difficult as working the right-hand side. Now, if you want, I could rework the right-hand side and we compare. We're going to get the same result whichever way we go, if we do it correctly. But I'm going to go with the the left-hand side. So when I do that, I'm going to assume at A that I have a positive moment at A and a positive shear force at A. This is not reactions and moments. This is shear force and bending moment. So I'm using the positive sign conventions for that. And we're not going to worry about axial force because we already talked about that for these beams. It's negligible. So to find these reactions, I need to find everything about my free body diagram. Right now, it'll be easier if I get a concentrated equivalent for that force. Since it's a triangle, it'll be 1/2 base times height. So 1/2 base, 20, height 2 kips per foot. That's a force of 20 kips. I'm going to probably sum moments about A, so I'll probably want the distance from A to the force. You remember our discussions before, the centroid of the triangle is either 1/3 the distance from the big end or 2/3 from the other side. And just to save me the fractions, I'm going to take my total length 20 and I'm going to multiply it by 2/3. So I'm going to get a funny number. I'm going to get 40/3. That way I won't have any loss of my numbers right now. So to find my reactions, I'm going to start by summing moments at A. So I'm going to use right-hand rule. So I'll sum moments at A. Make sure I'm in equilibrium. So with my right-hand rule sign convention for moments, what kind of moment is that? It is negative. And about A, what kind of moment does the 20 kip concentrated equivalent force create? Positive or negative? Negative. So I'll have 20 kip force times a moment arm of 40/3 feet. So my moment at A is equal to, it looks like it's going to be a negative value. Now we'll have to do some calculations. So that looks like that's 800 divided by 3. What's that? 266.7? Is that 800 divided by 3, Mr. Jafari? You sure? 266.7, and that'll be kip feet. And it comes out negative. What does that mean? Negative bending moment. Well, how do you think this structure is going to behave? Fixed at A, free at B, gravity load. How do you think it's going to deflect? Probably something like that. If you kind of look at it, that's kind of half a frown. Concave down, so that's negative bending moment. let's finish and get our shear. So if I sum forces in the y direction, and I'll assume up is positive, let's see what I have. I have a shear force that's up, that's positive shear at A. I have applied force that's down, minus 20 kips. So it looks like my shear at A is 20 kips. That's it. We got everything we need. So let's now come down here and draw the left-hand side. I'll make it a little bit bigger so I have some room to work with. So there's the chunk of my beam. It's X long. I've got a triangular load. Over here on the left side at A, I have a positive shear force of 20. And I got a negative moment of 266.7. So I assume positive, so the moment's actually in this direction. And then at the cut, I will assume positive shear force and positive bending moment. Now, the other thing I have to figure out right here is what's the intensity of that load? Well, now I need it as a function of x. So if you go back and look at this line, it's a straight line. You guys know how to write an equation for a straight line, right? You have a y-intercept, which would be 0, times the slope. What's the slope of this line? Rise over run. It's 2 over 20, which is 1 over 10. So this should be a function of x over 10 kip feet. And you can check it really quick. When x is 0, what do you get? 0. When x is 20, what should you get? 2. And it checks. You only have to check a linear line at 2 points, and then it's valid. So now I know the intensity of this load as a function of x, which is the distance that I've cut the structure. So when I go to find my equivalent force, what is it going to be? What's the area of a triangle? 1/2, right? Base. What's my base? X. What's my height? X over 10. So a little algebra tells me that that is going to be x squared over 20. And what's the position of the centroid of this triangular shape? Well, from the big end, it's what? Always 1/3 the distance, right? The distance is x, so this distance will be x over 3. So a little more to think about it a little more than before. So this free body now is valid for any distance x that I choose. Any value between 0 and 20, this will give me the appropriate concentrated force and the appropriate distance to it. So far, so good? So now what do? Does this body have to be in equilibrium? Yes, it does. So we'll start with our moment equation. I'll sum moments at the cut. Make sure it's in equilibrium. So again, I'm using right-hand rule. This moment is positive or negative? It is. Yeah, that's what I thought I heard someone say. Positive. Yeah, it's positive. This force, as I've drawn it here, acting down about the cut, positive or negative? Positive. And the force is x squared over 20. And the distance from the cut to that point is x over 3. So just to remind you, this is the force. This is the distance. So I come out here to 20. What kind of moment does that create about the cut? Positive or negative? Negative. Force is 20 kips. What's the distance from the cut to there? X. And then very down here on the end, I've got this moment, 266.7 kip feet. With my moment arm, that's positive. So you see now I have one equation that's a function of x. So I'm going to solve for my moment. So my moment at C now is a function of x, and I'll grab all my terms and try to go from the biggest to the smallest. So this becomes x cubed over 60, and when I change it to the other side of the equation, it becomes negative. Then plus 20x, and then minus 266.7. And each of those terms in that expression will be in kip feet. So there's an equation for moment as a function of x. Do I know values of this moment that I can check this equation with? Do I know the moment when x is equal to 0? What is the moment when x is equal to 0? Looking up here. It's that. And what is that? That's a negative bending moment, right? Negative 266.7. I've run out of space for my units. But so if I put in x equals 0 here, this cancels, and what do I get? Negative. Oh, that's good. That's a check mark. That works. Where else do I know the moment? What's the moment at a free end? There is none. So if I check the moment at x equal 20, it should be 0. You put an x equal 20 there. Tell me what the answer is. Somebody with a calculator. I'm guessing it's going to be 0. Let's hope it is. Did you get 0? Yep. That's another check. I like that. So now you should be pretty comfortable that this is correct. It matched the 2 points where you think you know the moment. In this case, at x equals 0, it's minus 266, and at the free end, it's 0. Now, if there were an applied moment here, it'd be equal to that value. We don't have one of those. That's pretty good. All right, let's proceed. Let's sum forces in the y direction. That should get us an equation for shear. So looking at my forces in the y direction, I have this shear force, which is down. So that's minus the shear. I have this force, which is down. So that's minus x squared over 20. And I have this force, which is up 20. And all of those should also have units of kip. So solve for the shear, and you get minus x squared over 20 plus 20. Bless you. There we go. Do we know something about the shear force in our structure? What's the shear force when x is equal to 0? Right here, we solve for it. 20. So does this tell me that when x is equal to 0, do I get 20 kips? And the answer is yes. What's the shear force out here on the free end? At x equal 20. It is 0. If you put an x equal 20 here, what do you get? 0. That's comforting. Now, look at these two equations, moment and shear. Do you see some kind of relationship between them? You might want to think about it on your trips over to Dunn Hall to take some kind of course over there. I think it starts with a C. Calculus, yeah, calculus. Think of calculus when you look at those relationships. Do you see anything unusual? Not unusual. Just, do you see anything? Something derivative related? Yeah, it looks like that if you take the derivative of the moment with respect to x, what do you get? The shear. Now that's anecdotal right now. That's just looking at these two. Later in the course, I'll show you a proof that that is true. But if you do look at this and you take the derivative, well, the derivative of that is this. Derivative of that is this. Of course, the derivative of constant is 0. So this checks too. So one great thing about these problems is you've got lots of opportunities by checking places that you know the value and also this differential relationship to make sure that you've got it right. It's rare that you have a problem that can almost self-check. That's pretty cool. Any questions about that? We're going to work more of these, by the way.